Can your software withstand all unexpected challenges that come its way? Here are 4 things I experienced firsthand that will weaken your program if overlooked, along with practical tips to make your software rock solid. Let's dive in. Imagine a simple program to convert student scores to grades. It takes the score between 0 and 100 and assign and print a letter grade. In this program, scores from 90 to 100 get an A, 80 plus get B, 70 plus get C, 60 plus get D, and 0 to 60 get F. Here is the basic Python implementation. First, the program reads the score as a float. Then it uses breakpoints with the bisect module to determine the grades. Now, let's see what happened with different inputs. If we input 90, everything works fine. We get an A. But what if we enter score? Boom! We get a value error because score is not a number. The program crashes. Not good. What about 101? It gives us an A, which is clearly wrong. The problem? Our program wasn't prepared for bad input. It doesn't handle numeric data or out-of-range values, leading to crashes and incorrect results. The key takeaway: always expect unexpected inputs. The solution is input validation. It is like a bouncer for your software. With input validation, the program verifies that the input falls within the expected space before using it. If not, the program provides clear feedback to the user, explaining why the input is unacceptable. To implement that on our program, we check if the input is a number. If not, when the conversion to float causes an exception, we give a helpful message. We also check that the number is within the valid range and give a message if it isn't. The next step is to take appropriate action, such as prompting the user to re-enter a valid input using a default value, or, if necessary, stopping the program to prevent errors. The general rule is to focus on the best user experience. For our example, we choose to prompt the user to input the value again. We use an infinite loop and break out when the input is valid. At this point, our program is robust against invalid input data. It gracefully handles unacceptable inputs from users. We improve the user experience by implementing proper input validation. It's crucial to implement input validation as close as possible to where the input is obtained so the user can get feedback as early as possible. For configuration files, it's good practice to provide the input validation code as a separate program that can run against configuration files to test them before running the actual application, especially background services. By implementing robust input validation, you can make your software resilient to unexpected events and provide a much better user experience. Remember, always expect the unexpected. Imagine this. We've added a new requirement to our program. We need to obtain and print a student's ranking based on their score. This ranking, a positive integer, is calculated using the getScoreRank function from the ranklib library. But here's where things get tricky. What if a bug in the library causes it to return a string instead of an integer? Or what if the library can't connect to the remote server it needs to retrieve the ranking? Our program must be robust enough to handle these potential issues. One golden rule when designing programs that make library calls: library calls can fail. To handle that, we check if the return value of the library call is a positive integer and raise an exception if it is not. Then we handle possible exceptions that the library call might raise. It's crucial to check and handle all side effects of library calls. You can find these side effects in the library documentation, so make sure to review and handle them accordingly. In summary, to make library call code rock solid, we need to treat it like input data and implement library call validation. If the result is invalid or the call raises an exception, provide clear feedback to the user, and take appropriate action. By doing this, we ensure our program can gracefully handle any potential issues that arise from library calls. To expand further on our example program, let's dive into the hypothetical ranking lib library and assume that it retrieves the ranking from a remote server. We have a predefined server host and port, and the getSchoolRank function calls the connect-to-server and getRank function, passing the predefined server information and the input score. For simplicity, when the return value is none, the connection error exception is raised. Otherwise, the returned value is the retrieved ranking. Let's look at the implementation of the connect-to-server and getRank function. It uses the standard library socket API to connect to the server and retrieve the ranking by sending the score in a request and receiving the computed ranking. Because the socket API is used, we have library calls and thus apply library call validation and raise a value error in case a problem occurs. A socket.error exception is also raised when there is an exception thrown by the socket library. This looks okay. However, the program is still sensitive to resource failures. For instance, the connection to the server using the socket API may never return, freezing the program. Similarly, the remote server can be temporarily unreachable or subject to transient errors, which will make the library return an error, even though waiting a bit will lead to success. We want to give a better experience to users. One thing to always think of when designing a program that accesses resources is that resource access can fail. Any running program makes use of resources in its environment and thus should be robust against resource access errors. Here are two approaches you can use to make your software robust against resource access errors. The first approach consists in handling the errors after they occur. It's like taking appropriate action on failed library calls. For that, use these measures according to the problem at hand. User feedback. Tell the user what's going on, what went wrong, and what will happen. Timeouts. Set a time limit for any resource access to complete and consider the access to have failed if the timeout is passed. To enhance our example, we specify a timeout of 5 seconds. This will make the resource access raise a socket.timeout exception if the timeout is elapsed. We catch it and process it as an error. When using a resource access library, make sure to check the information about the default timeout settings or systematically set a timeout value. Automatic retry. Some access errors are due to transient errors in the resource. This also includes timeouts. We can handle them without user intervention by applying the automatic retry measure. We retry the failed operation a given number of times. To further enhance our example with retry, let's retry 3 times and wait 2 seconds between retries. We wrap the connect to server and get rank function in a for loop, and after every iteration with error, log a message and sleep. Do not implement retry unless it is safe to do so. Any atomic operation is safe to retry. Do not retry if the resource access error is because of wrong access. When provided, you can make use of redundancy and automatically switch to backup resource so that the program can successfully continue its execution. In our example, we can use an existing backup server and automatically fail over to the backup server once all retries have failed with the primary server. The second approach prevents the resource access error from occurring. This approach consists of monitoring the resource, limiting the usage of the resource when access may fail, and notifying the user about the limitation. To illustrate this, consider a server that writes its log to a file and run on the same computer as other servers that share the same disk and also write some data to the disk. If the disk is full, logging and any other data writes by the server will fail. To prevent that resource failure, we implement a function to compute the disk usage. That function is used to monitor disk usage. Every 5 seconds, the program computes the disk usage. If it is above a cut threshold, logging is disabled to prevent filling the disk. This is graceful degradation of the server functionality. Before disabling logging, a message is written in the log to notify administrators that logging is disabled. Whenever this usage goes below the threshold, we enable logging. Monitoring should continue after graceful degradation of functionalities, and the functionalities should be restored automatically when the conditions improve. Monitoring runs concurrently with the server's core functionalities. What will happen to a software system if one of its components fails? One thing is sure, we don't want the whole software to fail in such a way that it is unusable or the provided service is interrupted. Any robust software should ensure that unreliable components do not cause the whole software to be unusable. In other words, you should consider any unreliable component as likely to fail and take measures to maintain usability. Here are measures you can implement to account for this case. Monitoring and alerts. Monitor the state of unreliable components to quickly detect bad states and notify the users and administrators. This ensures prompt intervention and triggering of the next measure. Graceful degradation. The design allows isolating the problematic component in case of a failure and letting the software function with limited functionality. This limits the impact of the failure. Automatic recovery. Ensure that the system must recover at some point, even with graceful degradation. Redundancy and failover. When it is crucial to maintain all functionalities, redundancy, replication, and automatic failover can be used to ensure that a healthy copy of the whole software or the problematic component can be used by users in case of failure. Note that this is useful only when the copies will not fail simultaneously. These measures are often coupled for higher effectiveness. To illustrate, say we have an unreliable program that is started by another program and is expected to run as a service until the end of the execution of the whole software. In case the unreliable program crashes, the whole software may be stuck because the provided service is interrupted. To remedy to that, we can implement both monitoring with alerts and automatic recovery by adding a watchdog thread that will monitor the health of the unreliable process and automatically restore it as needed. To wrap up, always keep in mind that input data can be invalid, library calls and resource access can fail, and unreliable component will fail. I faced these issues firsthand in many of my projects, and learning these tips has significantly improved the quality of my software. Follow this guideline when designing and building your software. If you receive data from outside, validate before use. If there are possibility that an operation never return, use a timeout. If there is an atomic operation that may have transient failures, use retry. If there's an error, notify the users. If there is a resource access error, use available fallback resource. If a resource can become scarce, monitor it and gracefully degrade functionality. If a software component is prompt to fail, consider automatic recovery. Additionally, also consider user notification, redundancy, and graceful degradation. Thanks for watching, and I hope you have gained valuable knowledge to make your software robust and provide users with better experience. Please like this video, subscribe, and check out the description section for additional resources to help you pursue your software engineering journey faster and easier.